Okay, so we been talking chapter 15 and we got into kind of solutions and we got into the idea of solubility and like dissolves like. So as we talked about last time, in terms of things like solubility, how molecules sort of interact with one another, um, they typically will interact really well with one another. They typically will be soluble with each other if they are using kind of the same intermolecular forces that they use with themselves. So things that basically share similar intermolecular forces typically are going to really kind of mix well, going to kind of work good together. And that pretty much means when we talk sort of about solubility, things are typically soluble if you got a polar and a polar sort of thing together. If you have an ionic and a polar thing, again, they could do sort of that ion dipole interaction. Polar and polar guys could do either dipole dipole or hydrogen bonding. And remember as well that nonpolar and nonpolar are all good as well. They both will be using dispersion forces. So again, things are going to work really well. You're only going to again sort of run into some problem when we talk about. I guess this should be soluble. When we kind of cross over polar and non-polar, as we talked about, really because they are using very, very different sort of intermolecular forces. They really have no way to, over sort of the long period of time, maintain that sort of connection or interaction. And they typically do not really mix really well together. We got into some concentrations and we talked about percent mass to mass, which is again our mass of our solute over the mass of the solution times 100%. Sort of grams over grams. There's also percent volume to volume is the volume of the solute, volume of solution times 100%. And we have percent mass to volume, which is our mass of our solute over the volume of solution times 100%. So as we talked about last time, you can definitely use these as just formulas as well. You also can, if you are given sort of the percent by mass or percent by volume, you can kind of convert those into conversion factors and take a more dimensional analysis sort of approach. Out of all these, really the one here is the one you really have to be careful with because it is very common in those type of problems. They will give you sort of the mass of the solute and the solvent sort of separate from one another. So you want to make sure that you are getting really the mass of the solution and not just one or the other. Then we finished up here talking about molarity, which is our moles per liter. Again, that is probably the most common unit of concentration. And remember, you can rearrange this, and liters would equal moles divided by molarity, and moles would equal liters times molarity. Remember as well that if you are using the molarity in a calculation, it is probably the best move to get rid of the big M. And again, kind of use both for the units there in your calculation. The number always stays with the moles part, and it's always 1 liter. And again, it's a very common error that people sort of just forget about the volume part of this sort of number. So you want to sometimes make sure you can kind of see it and take that dimensional analysis approach. Questions on any of that stuff there from last time? What's it? Wait, there's not one. Don't worry about it. Nope. All right, so let's continue on. How many moles of calcium ions and chloride ions are present in 42 milliliters of a 0.35 molar calcium chloride? Something else we talked about as well last time, sort of the relationship of the whole thing to its ions. So take a few moments here and see what comes up. There are a couple of ways you can kind of do this. You could figure out the concentration of the ions up front and then sort of do the molarity sort of calculation with it or the moles calculation. Or you could just do a regular moles calculation with the whole thing and then relate it to the ions at the end. Here, what I'm going to do is I'm going to just figure out the concentration of each of these ions in the solution. So if I had a calcium chloride solution, it would break apart into a calcium ion and two chloride ions. And as we talked about last time, if you know the concentration of the whole thing here, which in this case is 0.35 molar, you can really do almost like a mole-to-mole relationship to figure out the concentration of the ions. So in this case, it is a 1-to-1 relationship between the whole thing and calcium. And that means that the concentration of our calcium ions would be 1 times our molarity of the whole thing, which would give us 0.35 moles per liter of calcium. And again, I'm getting rid of the big M there because I'm going to use it in a calculation. When we look at the chloride, it is a 1-to-2 relationship here. That means in terms of the concentration, we would take 2 times 0.35 molar. And that will give us our concentration of our chloride ions in the solution. And in that case, it is going to be 0.7 moles per liter of chloride. So I just decided up front here just to get the concentration of the ions. And as we talked about, that's kind of the quick way you could kind of get the concentration of the ions. It's basically however many ions it breaks apart into, kind of do almost like a mole-to-mole relationship. And as you can see here, it's basically a 2-for-1 deal. You get twice as much chloride as you do calcium, so that solution is twice as concentrated in terms of chloride ions floating around as it is calcium. Now we really could just look at our molarity equation. Molarity, again, is moles per liter. In this case, we do have the liters part. We've got to do a conversion. We do have the molarity of everybody. So we really can rearrange this and solve for moles, which would be liters times molarity. Again, we do need to always, when we're using molarity by itself, we do need to convert our volume into liters. Otherwise, we do not get moles, but we get, as we talked about last time, we will get millimoles if you use milliliters here. So 1,000 milliliters is a liter, 0.0420 liters. I'm going to kind of set it up just dimensional analysis way. So for my calcium ions, I'm going to take my volume here. Going to use really my molarity as a conversion factor. So 0.35 moles per liter of calcium ions. Liters will cancel. And that's going to get me here. Looks like 0.0147 moles of calcium ions. I'll do basically the same calculation for my chloride. I got the same volume because obviously it's the same solution. And we're going to use our concentration of our chloride ions, which is 0.7 moles per liter of chloride. Again, the liters will cancel, so 0.7 times 0.042. Going to get us 0.0294 moles of chloride in this case. Also twice as much moles there. Any questions? So again, sometimes, as I mentioned last time, you are asked about the ions rather than maybe the whole thing. I would say probably most of the time you're going to be asked about the whole thing, but occasionally they may be interested in just the ions. Any questions on that there? The next thing we're going to talk about is dilution. And dilution is a really common process that is done. And it is usually done to really make more concentrated solutions concentrated and more dilute. And when you do a dilution, really the only thing typically is more solvent. And a lot of times that solvent is water. So a lot of times people say usually just add more water. But again, remember, water may not always be the solvent, but in a lot of cases it is. So when we add more solvent in this case, what ends up happening is the molarity will actually go down. And the moles, though, of the solute, the smaller part of the solution, before the dilution and after dilution will equal each other. There is no change. Why does the molarity go down? Because, again, molarity is moles of solute over liters of solution. And remember, once again, our solution is two parts. It is the solute and the solvent. So when you do a dilution, you're essentially increasing the solvent, which is increasing the bottom number here and making it bigger. When it makes that bigger, the molarity will basically go down because of it. So when you add that water or more solvent to it, you're basically decreasing the concentration. And here's one way that you could do it with a volumetric flask. This is a volumetric flask, means expensive, one marking, and that marking represents the volume. And if this was a 500 milliliter volumetric flask, typically 2 decimal places. So usually if you're going to do dilution, a little bit of water in there, some deionized water, your more concentrated solution goes in, top it off with some more water, give it a little mixy, shaky, and you should end up with a more dilute solution than you started with. That's a very fancy way of doing it. Most people just use a graduated cylinder, throw some water together. We could calculate the dilution by using this equation. And I would say that this is probably the most common equation used for dilutions. And this is M1 V1 equals M2 V2. This is kind of before the dilution typically. This is after the dilution. And M1 and M2 are the molarities before and after the dilution. V1 and V2. V1 is the volume of the more concentrated solution you typically use. V2 is the volume of the solution you're making. The more dilute solution is typically what that is. I would say nowadays, books like to use a more generic version of this equation, which is C1 V1 equals C2 V2. And really, C here is just concentration. So in reality, you could use this equation with you want. If you want to use like percent mass to mass on both sides, you could. But again, most people roll with M1 V1 equals M2 V2 because, frankly, molarity is usually the concentration that you're dealing with in most cases. So we kind of usually kind of refer to that one. But again, C1 V1 equals C2 V2 is the same idea. It could be any concentration unit and the volume here. Now, one of the things that sometimes confuses people is if you use this equation and you're using this equation here and you are doing a dilution, you actually do not need to change your volume to liters. It actually will work out okay if you are specifically using this equation. For that, for example, let's just say I was solving for V2, and if I did V2 would equal M1 V1 divided by M2. If I just put the units in, molarity for my first guy, if I left it in milliliters, and my molarity for my second guy, the molarities will cancel, and I will end up with milliliters at the end, and that's okay in most cases. Again, if you're solving for a molarity, maybe you're solving for M2, which would be M1 V1 over V2. And again, if I left my units in molarity and milliliters on top and milliliters on the bottom, they will cancel, and I will. So if you're specifically using the equation, you can leave it in milliliters. Sometimes it's helpful because a lot of times you are in milliliters. You don't have will self-correct itself here. If you are not using this equation though, and you're just using molarity and volume, you should definitely convert it to liters because again, you most likely want moles and not millimoles. Doing just a molarity non-dilution sort of thing that involves molarity and volume, definitely go liters always. If you're using this equation, you could leave it in milliliters. And by the way, you could also leave it in liters. So you can't convert it to liters here. The only difference is if you did liters, you would get liters at the end if you're solving for a volume. That's the only difference here. So you could definitely do liters here as well, but you could also do milliliters. All right, so let's take a look at one here. What is the volume of a 19 molar sodium hydroxide solution that is going to prepare a. Okay, so let's take a look. So basically what we got going on here is we have a bottle. Basically, 19 molar sodium hydroxide here, a more concentrated bottle. We want to make a new solution in a new container that has a volume of 1 liter or 1,000 milliliters, and it should have a molarity of 0.15 molar. So they're both sodium hydroxide here. There's no reaction happening. We're really just doing a dilution. We're taking something obviously that's more concentrated to something that's less concentrated. So we can basically use our dilution equation M1V1 equals M2V2 here. And once again, it doesn't really matter sort of which ones you call ones and twos, but like I said before, most of the time the more concentrated stuff is the ones. So here we would be solving for V1. We'll call these guys the twos. And I'm going to put it into my equation here and really solve for V1. So I'm just going to divide that to the other side. That's going to give me V1 is M2V2 divided by M1. Popping my numbers in here, M2 is 0.15 molar. I'm actually going to use milliliters here just because I like the number better. And we're going to divide by our original there, which is 19 molar. The molarities here cancel, which again is why it's okay to kind of use milliliters if you want. That will be what's left over. And that's going to give us 0.15 times 1,000 divided by 19. And you'll end up with something like 7.9 milliliters. If you did liters, 0.0079 liters, something in that ballpark is what you should end up with if you kind of did the liters into there. Now, what does that number really represent? Typically speaking, when you do solve for V1, which is most of the time the more concentrated solution, that is basically how much of the more concentrated solution you're going to take out, basically put into your new container. So basically we just calculated we need to throw in there 7.9 milliliters. Now remember, we want a volume of 1,000 milliliters. So in this case, we would use some deionized water. Should I put 1,000 milliliters of water in there? I should not, because if I did, I would end up with 1,007 milliliters or so. And that's definitely not going to be the right molarity. So it's really important to understand how much water you need to put in there. And by the way, with questions, that's also a very common question that's asked to you. And typically define, for example, the volume of the solvent or the volume of water. In most cases, you take V2 minus V1. We want to make a 1,000 milliliter solution. We already put in there 7.9 milliliters. That means that we need to kind of put in there with our 7.9 milliliters about 992.1 milliliters of water. So if I drop in there 992.1 milliliters of water, and again, give it a mix here. I am now going to have a solution that has a total volume of 1,000 milliliters or 1 liter, and it should at this point have a volume of, or a molarity of, again, like I said, very common question with much water to make it, how one, and how you figure out how much you should put in there with it. Question. All right, let's try another one here then. I think asked that question. What volume of water is needed to prepare 500 milliliters of a 0.25 molar calcium nitrate solution from a 5 molar calcium nitrate solution? So take a few minutes there and see what you come up with. So once again here, we're dealing with a dilution. We got basically calcium nitrate and calcium nitrate. One's 5 molar, one's 0.25 molar, less dilute solution. So kind of same idea as what we had previous. We got a bottle here of some 5 molar calcium nitrate. And that'll be like our M1. We want to make again a new sort of container, or that is a volume of 500 milliliters and a molarity of 0.25 molar. Once again, looking at our dilution equation, we're pretty much missing V1 again here. So we're looking for V1. And once again, we'll call these guys 2's on this side. And we will solve for V1, which will be our M2, V2, and M1. Popping it in there, 0.25 molar. Once again, I actually do not in this equation need to convert to liters. You can if you would like to. Once again, if you do convert to liters, you would just end up with an answer that's in liters rather than milliliters. We got 5 molar on the bottom. Molarities cancel. In my case, leaves me with milliliters. 0.25 times 500 divided by 5. That's going to get me 25 milliliters of calcium nitrate here that's needed. Again, if you did liters, 0.025 liters would be what you would end up with. Once again, that is not our answer in this particular case. That is, again, how much of the more concentrated solution we want to basically put in there. Here we are looking for how much water we want to add. So again, that is typically V2 minus V1 in this case. So the volume of the water is our final volume that we want to make, minus how much we already put in there. So we did 25 milliliters there. So obviously here we need something like 475 milliliters of water in this case to go in there. Also really important to make sure you read the question. Again, a lot of these are asking more about water and stuff like that sometimes than how much of the solution you do. Any question on dilution? I will say this, that formula that we just saw for the dilution, the M1, V1 equals M2, V2, is sometimes is where you not use. And we're going to talk about some solution geometry coming up here in titration. And you should not use that formula in this type of situation. So the best rule of is if it's a dilution, use that formula. If it's not, don't use it. Sometimes you may even see people online in places that will use that formula and call it the titration formula. It only actually works for a specific type of titration relationship. It does not work for everything. So don't use it anywhere else but a dilution. Everything else you should show with some stoichiometry, as we will talk about. Any questions on that there? All right, so speaking of stoichiometry, obviously we talked about stoichiometry regular. We talked about stoichiometry with gases. We should also obviously here going to talk about stoichiometry involving solutions. Basic approach is pretty much the same approach that we do for all stoichiometry problems. You want to balance the equation. You want to change whatever they gave you to moles. You want to determine the limiting reactant. If it is a limiting reagent problem, remember it may not always be, but if it is, you want to kind of do that. You want to calculate the moles that's required and then convert those moles into some other unit. Now, I will say probably in solution stoichiometry, you will in a lot of cases at 2 points along the way kind of use molarity and volume. So it is a very common way at sort of the second step, instead of using grams in the molar mass to get to moles, to use our moles is equal to liters times molarity. And once again, you definitely want liters here. And that's a very common place where you will use molarity. The ending part as well is a very common place that molarities oftentimes will kind of pop into play. And really at the end, if you think about it, here at this step, before you get to the last step, you will be in moles. So if you think about molarity, moles per liter, you will basically have this number. So at the end of the calculation, there's kind of 3 endings. You could use the molarity equation to actually solve for molarity, is a common ending. You could use the molarity equation to solve for volume if you do have the molarity. And you also could use not the molarity at all and just do a normal ending like we've done before, where you just kind of take moles to grams. So, you could also end it like normal that we've done before. So I will say in solution stoichiometry, especially when we get to sort of titration problems, kind of use a molarity up front on the second step and on the back end is a very common sort of ending. We'll take a look at one here together and kind of go through the steps and see how it's kind of similar, maybe a little different. Here we want to calculate the mass of sodium sulfate that must be added to 250 milliliters of a 0.2 molar barium nitrate solution to precipitate all the barium as barium sulfate. We also want to know how much barium sulfate we will make. So this really is a stoichiometry problem. This is one of the words. So we just want to do our stoichiometry steps, which obviously is we need an equation. So in this case, remember, as we talked about many times, you want to make sure that you get all the correct formulas down first, then balance the equation, right? So we will start with, we're making sodium sulfate. The sodium is +1, right? Sulfate is -2. So when we put those guys together, a little Na2SO4, we're going to react it with barium, which is +2. Nitrate is -1, so we need two nitrates in this case. So we should look something like this. That's our reactants in this case. Formulas. Also should hopefully be able to recognize look like that. All right, so plus minus. That is a double displacement reaction, right? So we always know in a double displacement, we're going to switch partners, which means again on the other side, we want to make sure that we do form the correct formula. Again, I'm not counting at this point. So when I take my sodium and I hook it up with my nitrate, I am putting +1 and -1 together, which gives me NaNO3 as the problem. When I take my barium, which is +2, and put it together with my sulfate, that is +2 and -2, which means I just need one of each. And that is really what we should end up with there in terms of proper formulas on each side. Any questions on that? So now that I have the proper formulas, now I definitely should make sure it's balanced. And in this case, it's not balanced. I got two nitrates on the left, one on the right, so I'll pop a 2 there for my nitrates. That gives me two sodiums on the right and two on the left. I have one sulfate on the left, one sulfate on the right, and I am good to go, right? Now we could roll through some of our solubility rules, right, to help us understand this. We know sodium is soluble in everything, so as soon as you see that, I know it is going to be aqueous, even though it started out as a solid, but it's going to, when it mixes together, it will be aqueous. Our barium nitrate here is soluble in everything, so I know that that should be aqueous. Sodium and nitrate together definitely should be aqueous. And sulfate here with the barium will be our solid in this case. So again, that is the problem. Well, all right. Which is basically the first thing that we want to do for the stoichiometry here. We then sort of think about what is given to us, what we want to find, and is it limiting reagent type problem, right? So in this particular case, we're actually looking for how many grams of this guy that we need. We are given for our barium nitrate that we have 250 milliliters and 0.2 molar. And the other thing we eventually want to find as well is how many grams of that guy, right? So we actually have two things we're kind of looking for. The first thing that tells me whether or not it is a limiting reagent problem, as we hopefully know, is when I look at the information given to me and I look at both reactants, the question you want to ask yourself is, can I get moles of both of them? And the answer is no, you can't in this case, right? So the only thing you could get moles of is barium nitrate. We have no information given to us about the geometry problem at this point. We don't have to worry about the limiting reagent. Obviously, if we were able to get some moles of each reactant, start out with then it's definitely not like a reagent sort of problem that you need to do. All right, so obviously we have molarity, we have volume. That's going to allow it here. And that's really what we want to kind of start with. So we want to maybe change some of these numbers here into more usable numbers. So I do need to convert my volume into liters because I'm going to use molarity with it. So 1,000 milliliters is a liter will give me 0.25 liters. I'm also going to take my molarity and get rid of the big M, and that's basically zero point 0.2 moles per liter when I do that. And again, I'm going to use that as a conversion factor. So step number 2, we're going to actually convert to moles, and we're going to use the molarity equation basically to do that. And moles is liters times molarity. So there's my liters, and my molarity is up there up on top. Moles per liter. Liters are going to cancel, and we will end up with 0.25 times 0.2, 0.05 moles of barium nitrate. So this is again where very commonly in solution stoichiometry is normally we're doing gram, the molar amounts to get the moles, but here we're doing volume and molarity basically. Any questions on that? Okay. At this point, we really are after two things, one reactant and one product. You can do them kind of individually. So I'm going to start with the sodium. Try to figure out how much sodium sulfate we need. I'm going to borrow this number, and I'm just going to flop the, maybe I'll go this way. I'll do it both. See it. All right. So for my sodium sulfate, all right, so third step here, I want to figure out my sodium sulfate. I'm going to take the moles that I calculated, 0.05 moles of barium nitrate. I am now going to do my mole to mole relationship between the two things I'm interested in, and that is my barium nitrate and my sodium sulfate in this case. And looking at the equation, it is a 1-to-1 relationship between the two. So that makes the math not too difficult, hopefully. So 1 mole of sodium sulfate up on top, 1 mole of my barium nitrate on the bottom. The barium nitrate is going to cancel. We're going to now be left with 0.05 moles of sodium sulfate. That is basically our third step. We're interested in grams. So our fourth step here for this part of it, the grams of it, we will need the molar mass. So of the sodium sulfate, so that's 2 times 2299 for the sodium, plus 3207 for the sulfur, plus 4 times 16 for the oxygen. That's a molar mass from the periodic table, about 142.1. Again, we're going to use that as a conversion factor. So we'll take our 0.05 moles of sodium sulfate. We're going to use the molar mass from the periodic table to figure out how many grams that represents. So grams are going to go up on top. And that will tell us here, looks like, if I hit the right button, it looks like something. Maybe like a 7.10 grams of sodium sulfate. A reminder that this is a reaction, so this is not a yield or anything like that. That's really, if you're going to do this reaction, you would need to scoop out, based on what you're starting with the barium nitrate, 7.1 grams of sodium sulfate to put it in there. First off, any question on that? So again, as you can see, basically the same 4 steps as we've done before. In this particular case, we're also interested in the barium sulfate, so I'm going to kind of re-up here step 3 and 4 for my other guy that I'm looking for. I'll do that big in red. So because we had 2 questions in this problem, I'm going to redo step 3, but now I'm going to look for my product, which is my barium sulfate. So we can again start with our moles that we calculated in step 2. We could actually even use the moles of the other reactant we calculated as well if you wanted to. Barium nitrate. Now we're going to do the relationship between barium nitrate and our product, which also looks like a 1-to-1 relationship. That's a good relationship there. 1 mole of barium sulfate will give me 1 mole of my barium nitrate. And that's going to give me 0.05 moles of barium sulfate. By the way, that would be a yield in this case. That will yield the barium sulfate in moles. But again, I want it in grams, so we're going to do the 4th step, which is how many grams of my barium sulfate. Once again, we will need the molar mass there from the periodic table for barium sulfate. Barium is a 137.3 plus 3207 for the sulfur and 4 times 16 for the oxygen. Looks like about 233.4 as our molar mass. So to finish this one up here, we'll take our moles from the previous step, now use the molar mass for barium sulfate for the periodic table. And that's going to get me about grams. Any question on that there? So this is again basic stoichiometry step, and in this case we did finish like we normally do with the molar mass, but very common solution stoichiometry, you kind of finish with molarity as well, and we'll see some of those next time, I think. Yeah. All right, I think we'll get up there.